We can start. Yeah, okay. So we proved some convergence result for gradient descent, and we proved results like this for the PL condition. Let's say PL is more a little bit generic than convexity, and here we prove that fxt minus infimum of f is less than equal to 1 minus gamma mu t fx0 minus infimum of f. Okay, so it converges to the infimum at this rate, and this rate is actually linear. So the power of t does not mean that it's exponential, because when we look at rate of convergence, we look at the previous one. So so actually it's gamma mu fxt minus infimum of f. So when someone asks you to show what is the rate of convergence, then you will say the rate of convergence. So let us say this is t minus 1. Okay, then you will say the rate of convergence is this, which is linear. So we have proved this. We are doing things rigorously, which is good. We need to do this once. Now, last time where I was is sum of functions, and I did some results, so I will just quickly just state those results. So theory for sum of functions. So what we have done are very generic cases, okay? And what we did in the last class, the little bit of what we did is let us focus on some special cases where f is sum. Okay, so f could be sum of some fi. Okay, and this is what you see a lot in machine learning. Okay, so this matters as a special case. This matters a lot. So we can define. So we have defined this in the last class. Is this 1 over n sum of fix? So this is how, like, we also normalize this a little bit. So 1 by n, and then we call this functions of this form as sum of functions. Okay. So and we have seen, okay, it could be sum of convex also. Okay, so it could be sum of convex functions and sum of L max smooth also. So if these are convex, then we call it sum of convex, obviously. And if this is L max smooth, okay, so these are just the terminologies that we have, right? So if it happens to be L max, I mean, if each of these are Li, the ellipsis smooth, okay, so these are Li smooth. Okay, I have defined all this in the last class. Then we can define L max smoothness also by taking a max of the Li. So overall, this guy will become sum of L max smooth. So we have proved this in the last class. Okay, for detail you can see there. So sum of L max smooth. And similarly, we can also define average of the Li. Okay, so in this case, L max is obviously max of Li, and we can also have L average smooth. So in this case, L average is defined to be 1 by n sum of the individual Lis. We have shown in the last class that if Fi's are Li smooth, if Fi's are Li smooth, then F is the sum, right? Then F is L average smooth. So we did this. All these were easy proofs in the last class. Then we said that since the machine learning regime is a stochastic one, because these sums are considered only partially, so hence the gradient that I compute, so this sum is over some examples, and I consider only batch of those. So hence this f becomes very, I mean not the complete f, but since I choose these samples randomly also, so we get an approximate f for which I will do the gradient descent. So hence we will get into a case where we will have some randomness involved. So we recall a few things for that. So this obviously denotes expectation. I'm just copying this, but obviously all these are known. Okay, so expectation of x condition on y. So these are the things we have seen in the probability class as well. And then variance, obviously variance of x is expectation of x minus expectation of x whole squared. Okay, so these three things are needed for the moment. There is one result, lemma 4.6. So these notes are in the Moodle, so you can check this. So for all y in Rd, this says that variance of x must be less than equal to expectation of norm of x minus y squared. And this is a simple result. You start with the variance of x, and you expand this, okay, and you expand this and use the so first let us look into this expectation of x minus expectation of x whole squared. Okay, so it's like norm, okay, squared, and if we expand this, then we have norm x squared, or okay, so y is also introduced here, minus y and plus y, right? So x minus y. So let us do this one more step, x minus y and plus y minus expectation of x whole squared. Now we do this a plus b whole square. So this is norm of x minus y whole squared plus norm of y minus expectation of x whole squared plus 2 inner product of x minus y, y minus expectation of x. And we will take expectation now on both sides. So taking expectation, then we have v of this, which is the variance of x, and this is so here expectation applied here, and then okay, let us apply expectation on both sides. So expectation of norm x minus y squared minus minus y plus y, or was it okay some, because for the other guy it seems like we will also get so once we put an let us do this in our way, one step where there is some simplification going on here. So y minus expectation of x, and then is squared, and then plus 2, and then expectation of x minus y. Y is a scalar here, so, and then this is y. So we can put this in which form we prefer, y minus, okay, so we put this, so we reverse this guy then, okay, so y minus expectation of x, and so let us do this, and then we put a minus here, obviously, minus, and then y minus expectation of x, then it becomes a norm of that. Okay, this becomes a norm of y minus expectation of x whole squared, and this guy was supposed to be plus. So then we have minus of y minus expectation of x whole squared. Everything seems okay, right? Minus, yeah, there seems to be a little bit of mistake here, but it seems fine. Okay, let us, anyway I will get 1 minus here, and then I will claim the inequality. So this is minus expectation of something positive. Okay, in the notes it's given minus, still minus 2, which seems wrong. Y minus expectation of x. Now this guy is less than equal to 0 because it's an expectation of a positive quantity. So average of a positive quantity will remain positive. So this is positive, so this is necessarily negative. So this must be less than equal to expectation of norm x minus y squared that we wanted to prove. So now what we will define is same way what we did. So we will now define smoothness, but it will be expected smoothness. Okay, expected so then we have a lemma 4.7. So if assumptions, let us say sum of L max smooth and sum of convex hold, then F is L max smooth in expectation, in the sense that, so we define that what exactly it means. So for all x, y in Rd 1 by 2 L max, and then expectation of grad f I y minus grad f I x is less than equal to fy minus fx minus grad f x y minus x. This is both the definition of L max smooth and also a result that one has to prove. So if we prove this, then I mean we will use lemma 2.29. So yeah, so this was the usual result from the L max smooth and convex, L smooth and convex, right? So recall lemma 2.29 in the notes, and here we were given that 1 by 2L grad f y minus grad fx is less than equal to fy minus fx minus grad fx y minus x. So this is the lemma. We have proved everything so far in the notes. Okay, so we must have proved all this, and that's it. So this is what we are supposed to use, and Li's are less than equal to L max. Hence 1 by Li will be greater than equal to 1 by L max. Right. Okay. So for each of the Li we can, for each of the Fi we have this. Okay, because Fi's are like Li smooth. So so for each of the Fi's we can put this Li here, but then 1 by Li is greater than 1 by L max. Okay, so hence we have the result, because 1 by L max will be somewhere here. Okay, and this is less than equal to 1 by Li, and then these guys are less than equal to this, which is what we want. Okay, and to bring in the expectation, we may have to do the sum. Okay, so this is the plan. So each Fi's are L smooth. Okay, so so I will use this, let us say. Okay, so since, okay, I mean, let me do it. Okay, so since each Fi are Li smooth, so for each of the Fi this certainly holds. So this implies, so, and then 1 by Li is greater than 1 by L max for all I, because L max is the maximum of all Li. So with this, now I will write down. So then I will have 1 by 2 L max grad F I. L max applies with F, right? But it can also apply with Fi, that's fine. And we are supposed to bring in expectation also. So I will need a sum also, right? Okay, let me write down first, and then grad Fi x, and this guy must be less than equal to 1 by Li of the same thing. Okay, so this is grad Fi y minus grad Fi x, and now for individually this thing holds. This is less than equal to Fi minus Fi x minus grad Fi x y minus x. So we have this, and what we are now supposed to do is to do the sum, because these guys are in F, and what we have are the components. So if I sum this n times, then I will get sum of Fi, which will be Fy, sum of Fi x will be Fx, similarly for the gradient. And here the sums that I will have will be seen as an expectation, because it's in the norm, right? So right, so let us do that. So now taking the sum, right, of on both sides for I equal 1 to n, I hope I'm not deviating anywhere. That seems fine. And we are also like taking 1 by n, so that this guy becomes like an expectation. Okay, and multiply by 1 by n. Okay, let us see what happens. So so 1 by 2 L max comes out, and this we have is, and 1 by n also we multiplied, and then we have the sum of these guys, f grad Fi y minus grad Fi x, and this is less than equal to, now this is evidence, right? So let me do it anyway. So Fi x, and then all this is 1 by n, plus sum of Fiy plus minus, and then inner product of the sum can go inside, right? Sum can go inside, and not just that, sum can go inside the gradient also. So I can write this as grad sum of Fix, right? Because grad is a linear function, right? So, and then y minus x. Okay, we did the sum and we multiplied by 1 by n. Although I don't know how n on the right hand side will, no, okay, the way it was defined, right, the sum, it is, the whole thing is actually f. Okay, so that makes sense. Okay, and this guy becomes an expectation, right? So this is an expectation of this guy. So basically some form of average. Okay, so 2L max, expectation of grad of Fi y minus grad Fix squared, and this is less than equal to, now these guys are f plus, I think AC is too cold maybe, and then we have, yeah, this becomes f, so grad f minus, okay, this is what we were supposed to prove, right? Okay, so there is another lemma, but that can be seen as an exercise. In fact, the hint is there in the notes itself. So if assumptions sum of L max smooth and sum of convex hold, then for every, you see the charm of working on board, even if it takes 30 minutes more, I mean, it's much different than what you see on slides. Okay, so for every x in RD and every x star in argmin f, we have, so this is a result that is left as an exercise for you. Okay, you can try a few things on your own also. So we have this result 1 by 2L max and expectation of norm of, okay, gradient of Fix, and then minus gradient of Fi x star norm squared is less than equal to Fx minus infimum of f. So this is a result that is left as an exercise. In fact, the exact hint is told to you that apply lemma 4.7 with x equal to x star, y is equal to x. So it's supposed to be like easy one. Okay. Then let us go into defining minimizers of some of these functions, right? So how do we relate minimizers, right? So there could be cases where minimizer of Fi are the same, right? That could be the very easy one, right? So each Fi minimizer is x star, let us say. Okay, so those kind of cases can happen, or their minimizers are very close. Okay, so how do you characterize minimizers of sum of functions? So then we go to this section which is called controlling the variance. definition. So this is 4.9, and so consider sum of functions. We say that interpolation holds if there exists a common x star in Rd such that Fi x star is infimum of Fi. That is, x star becomes a minimizer of all the Fi, okay, for I equal 1 to n. In this case, we say that interpolation holds, and it holds at x star. Okay, this can be a lucky case, but apparently in some of the neural networks it is found to be true. Okay, so that's why people study this, right? And lemma 4.10. Consider sum of functions if interpolation holds at x star in Rd, then x star becomes the minima of f. Then x star is in the argmin of f. In other words, minima of the Fi's is also a minima of the f. So let us prove this. And so as I said, like interpolation whole means for all Fi, x star is the minima of Fi. So proof. So since the interpolation holds, right? So I can write this directly without. So what is Fx star? This is 1 by n, because f is sum of functions. So this is 1 by n, sum of Fi x star. Sum of, this is by definition, sum of Fi x star I equal 1 to n. And this is equal to infimum of Fi, obviously, and then this is less than equal to any of the x. Okay, that's fine. So I can write directly. So 1 by n, and this is Fi x for any x. If I put any random x, then it will increase the Fi values. Okay, I equals 1 to n. And this is Fx. So basically what we have shown is that Fx star is the lowest possible value, because for any x you take, Fx happens to be always larger than or equal to Fx star. Hence x star is the minimum possible value for Fx. Okay, so this implies x star must be the argmin, okay, the argument at which the minimum is achieved, the x at which the minimum was achieved. So this is why it's called argmin. Now let us look at some examples of sum of functions, so in some practical examples. So the first one would be least squares. Example, this is least squares. So in least square, obviously we are talking about regression here, and in this case the cost function is given by 1 by 2m, and norm of phi x minus y squared. Okay. So here I can see phi as see this as a sum of the phi functions. So I can write this as follows. So here phi could be seen as phi I equal 1 to n, and y could be seen as yi I equal 1 to n. And in this case, the fi's will be half of phi I x minus yi squared. Okay, so I can construct a fi, and then the sum of these fi's must give me the fx. Okay, so in this case, obviously, for the interpolation to hold, what we are looking for is that there is an x star for which this becomes minimum. So minimum value of a square is when the argument is 0. So in this case, the interpolation will, so interpolation holds if there exists x star such that we have phi I x star minus yi is 0. And this is essentially a phi I is nothing but a hyperplane. Okay, I mean the phi I star, phi I x star. Okay, basically whole thing will be seen as a hyperplane. So we are asking for hyperplane that passes through these points, right? For all I. So this means that we can find a hyperplane passing through phi I yi, right? So this was one of the problem, right, where f is seen as a sum of some small functions, right? So you can kind of like expand this if you want. Okay, so if it's a linear, then it's like this matrix type, right? I don't know how big is, oh, there must be m somewhere, right? There is all n anyway, so phi are n of those. So it's essentially you are doing this kind of matrix vector multiplication, and then these are the y1 y2 you have. So this is the problem, and what you are saying is that phi 1 x y1, right? So phi 1 I do a dot product, so that's why I write x is equal to y1. So that's my first fi, f1, and then my second function is phi 2x y2. So that's my second function, and obviously all these error must be like combined, right? So that's why we have some of these functions, right? So a good question right now is, if you sum this up, right, do you really get this or not? Because the way it is written, right, it is a 2 norm, right? So the way it is overall is that this is a norm on a vector, right? So each time you are doing this, so this is your first component of the vector, this is your second component of the vector, and so on. And on this vector you have the norm squared. Okay, so usually it's 2 norm squared. then this boils down to, so this is 2 norm, right? So this is this squared plus this squared and so on, right? So this is phi 1 x minus y 1 squared, okay, plus phi 2 x minus y 2 squared plus dot dot dot, okay. So these guys are the FIs that we are talking about, okay. These are the FIs. These are the FIs. Still worried to see this M here, because nowhere I had like, if there is an M, then it should be perhaps these phi. Maybe these are an N. So maybe this is N. Okay, there may be a mistake. I find a lot of mistake in this report. So that's how it is. Okay. So if I add these, each of these, and take 1 by n, and there is a half already. So 1 by n, sum of these 1 by n and half, then I do get this. Okay. So this is indeed, f is, you can check that f is indeed sum of, so f is indeed 1 by n, n by 2n, sum of fi, where fi's, as I said, are this only, okay, which is coming from that derivation, okay. So what we want to say here is, many problems that you will see in machine learning especially, because machine learning by nature will be like this, because what happens is you have many like each time you apply this on X, and then you make sure that your output is something, okay, and next time you apply on the input, and then you say output is something. So so it makes sense, okay, because the losses are calculated for each sample and the corresponding output. So that gives me one F1. For the second sample comes, I apply, it could be the same Fi also, okay, it doesn't matter, but I have some another loss which acts on Y, and then because the Y changes there, right? So that's why it's very natural that all machine learning problems are kind of sum of functions anyway, okay. Okay, so for example, if it's a neural network, then also it's the similar, okay. So example 4.12 is neural network and interpolation. So a neural network can also be written as, if it's indeed a regression problem, then obviously neural network or loss will be very similar to what we have. It's just that the phi will act like some neural network. Okay, so in this case, the only difference would be is that phi will be highly kind of nonlinear, and so-called neural network. So for the moment, you may not have to really worry about that, but the point is that for each x, okay, the phi will be applied, and then for that x, I have to say what was the output, right? So the way things are is x1 must match with y1, x2 matches with y2, and so on. So it is natural that, let us say, let us distinguish that from this. So let us say this is phi nn. So this is some function, okay, phi nn is a neural network. It takes x1 and phi nn, it takes x1 and it must be y1. Phi nn next time it takes x2 and output is y2. So this is again a sum, because the losses are sum of the losses. So the loss function in this case we call it f, is nothing but sum of these losses. Now it depends, if you just take a difference and just take a mod as a error, or take a difference and take square of the norm as an error, it's up to you. The norm itself can change in many ways, but so this is basically phi x1 minus y1, it's exactly the same, okay? So since I'm using a square one, I can put a square here, then phi x2 minus y2 squared, and so on. Sometimes in neural networks, the output themselves may not be a scalar, okay? So those things also one has to be a bit careful, because phi itself can be a function that takes from Rn and it outputs Rd. Okay, let's say if it's some kind of a vector as an output, you have to predict. Okay, then in that case, these will be even some small norms here. Okay, but at the end of the day, what we are trying to say is that neural networks are also like sum of functions. So this is like some fi, this is some, so this is some f1, this is some f2, and so on. Okay, so this can also be seen as sum of in fact almost all machine learning problem will be like this, sum of functions, all supervised machine learning. Okay, unsupervised may not be, so what we have seen is that if there is a local minima, I mean a minima for each of these, there is x star, then that becomes a minima of these fx. But that's when interpolation happens, right? So interpolation means that the same x star becomes a minima for all the fi, but that's a very wild assumption, right? So in general, it may not be the case, and hence we will talk about the proper difference. Okay, so these guys may have local minima that might vary. Fi may have some xi star and so on. In that case, then we will say, okay, with these local xi star, how far it will be from the global x star. So for the neural network case, it was found that this interpolation actually happens. Okay, so if I remember last, I should have a reference maybe. So I can cite a reference where you can have a look, and maybe, so 24 and 23, these are the neural network case where these interpolation is seen in neural networks. Okay, so 24 and 23. So 23, let us say first. So this is Liu et al. And here towards a theory of optimization for parameterized networks. Okay, so towards a theory of optimization for over-parameterized networks. Systems. Okay, so that's 23, and 24 is the power of interpolation. Okay, so that's M. Belkin, and this is the power of interpolation. This is good, important. That's why I'm writing this, because neural networks are the main thing these days. Okay, so it's good that interpolation happens, right? Then much theory can be developed there. So ... the title is more, and this is in ICML 2018 International Conference Machine Learning. So okay, so that's good. That's why we are doing this, right? Because interpolation happens, meaning there are these local losses, but then kind of they have this I mean they have this same minima. So it should be like this maybe. Okay, so this loss, and then the function which is sum of these maybe also have these. Okay, so this is an interesting thing, right? Individual there is an x star for which there is a minima for each of these, but then that will be the global minima. Okay, so as I said, now this is a very special case, and this happens for over-parameterized network. Now, this may be good in many cases, may not be good in some cases. It depends. Like, we have to kind of look into this. It may be some architectures which need over-parameterization, right? So, okay. So in general, we will not have interpolation, right? So in that case, we can define a something called function noise. So this is function noise. So we define the function noise as delta star f. This is defined as infimum of f minus 1 over n, infimum of fi, I equal 1 to n. So as you can see, in this case we are not sure, right? Because if interpolation happened, this will be 0, delta star f is supposed to be 0. But in general, it may not be. So we will characterize the gap like this. So with this, we can prove a lemma, which is 4.15. And that says that delta star f must always be greater than equal to 0. Okay, delta star f supposed to be greater than equal to 0. Okay, so we start with the delta star f, the definition, and see where we go from there. So delta star f, which is infimum of f minus 1 over n, infimum of f equal 1 to n, and this is so let us say x star is in the argmin. So assume x star is the minimizer of f itself. Okay, so let us say that. But then for those x star, these guys may not be kind of 0. Okay, so in those cases it will be greater, right? So the greater, right? Because now if we do it at, did we substitute already x star, or yeah, we can write one more step, let's say. So this infimum is achieved for the x star. So this is fx star, that's fine. Minus 1 over n, and then now infimum of f will be in general, if I put fi, right? Sorry. So if I put fi x star, then those are likely to be bigger. And since those are likely to be bigger, the after subtraction is going to do what? It will be greater or less. Here we have to see, right? So what I'm trying to say is this. I will replace this by fi x star. Okay, and here I'm talking about infimum of fi, right? So infimum of fi is less than or equal to fi x star, because x star may not be the minimizer of fi, right? So in that case, it's likely to be greater or equal. Okay, so fi x star is greater than, and then what we, if we take the negative of that, then it will be greater than equal. Okay, so this is the inequality we are going to use. So this will be essentially greater than or equal. Okay, because other way. So this is greater than equal. So infimum of fi minus of infimum of fi is greater than or equal to minus of fi star x star. And why this should be? I mean, this is just f now, right? So this is now f star. So this will be 0 overall. Okay. So this is f x star minus fx star, because the way f is defined is 1 by n sum of fi. Okay, so this goes to 0, right? So eventually we prove that delta star f is greater than equal to 0. And the another result is it says that interpolation holds if and only if delta star f is equal to 0. Okay, so that's the second part. So the second one is interpolation holds if and only if delta star f is equal to 0. Okay, so let us try to prove this. So let us assume that interpolation holds, and then we will prove delta star f equal to 0. Okay, so let the interpolation holds. So this exactly means that x star is in argmin of fi. So that is x star is in argmin of fi. And in the lemma that we have shown is that if the interpolation holds, then x star is also in argmin of f. Okay, so that's the initial lemma that we showed. Okay, so according to lemma 410, we have x star is in argmin of f. Okay, so with this we have delta star f which is defined to be infimum of f minus 1 over n infimum of fi. Now this is fx star minus 1 over n fi x star I equal 1 to n, and this is fx star. So this part was easy. Okay, it just followed. So indeed del star f is 0. And now consider the other case. So this was interpolation holds, and this is the other way. If let delta star f equals to 0. So what we are supposed to prove now is that if delta star f is, which is this, is equal to 0, then it's necessarily the case that x star, which is in the argmin of f, is also in the argmin of fi. Okay, so let us assume that x star is in argmin of f, and we have to prove that it actually interpolates fi also. Okay, so let x star be in argmin of f, and in that case, so what we have for a start is that we are already given that del f star equals 0. So let us start from there only. Okay, so 0 is del star f, and this is fx star minus 1 over n sum of infimum of fi. Okay, and we put this in the sum now. So this is equal to 1 over n sum of fi x star minus infimum of fi, and this goes into sum I equal 1 to n. Do that, there is no problem there, because fx star is nothing but 1 by n sum of fx star. So that's what we have done. We have replaced the fx star by 1 by n fi x star, and what we are supposed to say is that x star interpolates, right? So, and we are given that these guys are, the sum is 0, right? But what do you see about these individual terms, right? What are these individual terms? Are these positive, negative? What do you think? Positive, right? Sum of positive values will be 0 if individual terms are 0, right? So that's easier argument now. So these guys, because this is the minimum that you can have, and this is some x star, this may not be optimal for fi. So each of these guys are greater than or equal to 0. So sum of positive numbers being 0 implies individual terms being 0, right? So this proves that indeed x star interpolates, right? Meaning x star is a minima for all fi, right? So this is for all I. Okay, so that's our proof for if and only if. Definition 4.16. Now we want to also define gradient noise. So what we have done is something called function noise. So delta star f was defined to be a function noise, right? Now we will define something called gradient noise. So let us consider, let f be sum of L max smooth function, and we define the gradient noise to be, define the gradient noise to be sigma star f is defined to be infimum of x star arg min f and then variance of grad f I x star. And here when we are taking variance, then obviously we are treating gradient as some random variable. Okay, so essentially grad f is becoming random because of the points on which it's being calculated. Okay, so this is where variance is obviously defined to be, we have already defined this, right? So is expectation of x minus x whole squared. Okay. So for this, the gradient noise, what are the properties we can have, right? So this lemma suggests some properties. So first one is, so these are all L max smooth cases. So sum of L max smooth. So the first result says that is sigma star f is greater than or equal to 0. And if we have sum of convex functions, then sigma star f is variance of grad fi x star for all x star in arg min of f. So this is, if you have sum of convex functions sigma star f, then yeah, this is how sigma star f will be. Okay, that's when we have x star which is in the arg min. Okay, so if x star is the minimizer of the function f, then you want to know the variation in your gradient for each of the individual fi at x star. Okay, so that's why we have these variance noise. Okay, so the problem is that yeah, I mean, first of all, the interpolation may not exactly transfer in this case, and then yeah, so these fi itself yeah, these fi itself may not be the perfect ones. So anyway, like we will see this in the proof how it will be used. If interpolation holds, if interpolation holds, then sigma star f is 0. Okay. So if interpolation happens, then the variance will be 0, the variance in grad fi. I mean, if it was a definitive case, then gradient itself vanishes, right? Because x star will be the infima of fi, and in that case you can immediately say that if fi are differentiable, then you can say grad fi becomes 0. Now in the cases where you have randomness, then instead of saying grad fi is becoming 0, now you are saying variance of that is 0. So the first one is kind of trivial, because the way variance is defined is that it's going to be positive. Okay, so that's fine, the variances are positive. So first one is trivial. Second one we can try to prove. Okay, so the first one is trivial because the variance of grad f I x star is non-negative. So each of these are non-negative, and the infimum of non-negative number is non-negative, right? So overall you are supposed to do also infimum, right? But infimum of non-negative numbers are non-negative, so that's done. And the second is if we have sum of convex functions, then sigma star f will be variance of grad fi x star. So essentially what seems to be that it seems to have no role here, right, infimum, because we are saying directly that sigma star f is variance of grad fi x star. This is infimum over all x star in argmin. Because it's convex, so minimizer will be kind of unique, right? So there is no point in taking kind of all infimum over all possible. So that's the reason why it seems it just goes away, right? The unique minimizer, right? So there will be just one x star and that's it, right? So let us try to do this then. So let us assume that there are two minimizers. Okay, so let x star and x be in the argmin of f, and let us show that the variance of grad fi x star is variance of grad fi. So if we show that, like what you're saying is that essentially what we're saying is that this has no role, because if it's sum of convex, then kind of they have unique minimizer. So what we are trying to say is that let us pick, in case there are two of them, x star and x prime, let us pick, and what we will show is that both the variance of for both x star and x prime will be the same. So essentially this is indirectly trying to say that okay, there is no role of these guys, because no matter how many infimum over how many x star, x prime, whatever we are going to do, they are all equal only. So this has no role, and this is what we are supposed to prove here. So, and what is important to note is that x star and x prime, what we have assumed here, right, x star and x prime are argmin of f, not fi. Okay, so this x star and x prime argmin of f, the minimizer of f, and what we are trying to claim is that the variance of the grad fi at x star and x prime are the same. Okay, so essentially if x star and x prime are minimizer of f, then these individual fi's which are convex, because this is a sum of convex. Okay, so these gradients these also, the variance of these are the same. So okay. So in this case, we have assumed, right, L max smooth and sum of convex. So we assumed L max smooth and sum of convex. L max smooth was part of the initial definition, and then this is for this part, sum of convex. Now we can use the expected smoothness that we have defined before, and using that, so use the expected smoothness. So expected smoothness was defined for L max, right? L max smooth. So for that, we immediately get 1 by, if you can recall, 1 by 2 L max, expectation of gradient of Fi prime minus Fi x star, and this is less than equal to Fx prime minus minus infimum of F. Now x prime was also infimum of F, so they cancel. So they become 0 eventually, right? So we have this, we use this expected smoothness. So this is less than or equal to 0, but again is the same argument, right? These are positive quantities. So expectation of a positive quantity cannot be less than equal to 0, so it has to be equal to 0. But then each of the terms are positive, so each of the grad Fi x prime must be equal to grad Fi x star. Okay, so this implies expectation of grad Fi x prime minus Fi x star equals to 0, and furthermore this implies that each of the grad Fi Fi x prime is equal to grad Fi x star for all I. Yeah, we have this L max smoothness given. Yeah, that's how we are applying this expected smoothness was for L max smooth. We have used proved this lemma from where we get this. Okay, in slightly before we have done this, and right. So norm. So we got an even stronger condition that these grads are equal, right? So obviously variance will be equal also. Okay, so this implies obviously variance of grad Fi x is equal to variance of grad Fi x bar for all, and that's exactly what we were supposed to prove, right? Yeah, we have used this once again lemma 4.8. I will immediately like cite this lemma, and then we can lemma 4.8, right? So here. Yeah, so we assumed both sum of L max smooth and sum of convex was also needed. Then for every x and its x star, we have x star is in the argmin. So in this case, it also happens that both are in argmin. So then we have 1 by 2 L max expectation of Fx minus infimum. Right. Okay. So then what is your question? So we apply directly this lemma 4.8. What exactly you wanted to say? Actually, this itself is the definition. Okay, so if we see the So when so we say that something is Lmax smooth is when this is, I mean, yeah, I mean when this is satisfied basically. So what I'm trying to say is that this implies this. Okay, so maybe there is a confusion with the fact that so I will say just use lemma 4.8. Okay, so use lemma 4.8. So what lemma 4.8 says is that if you have Lmax smooth and sum of convex, then you have this. Okay, and this criteria itself is called expected smoothness. Okay, so we have, so this we proved already, so we don't have to, yeah. So variance are equal, and third one is this, right? If interpolation holds, then sigma f star equals to 0. So if interpolation holds, meaning x stars are the minima of each of the fi. So if it was a deterministic case, meaning these were not random variable, then x star interpolating would mean that x star is the infima of fi, meaning all these gradients would vanish, right? And in this random variable case, we are saying that, oh, gradients are now supposed to be random. So what can you say in that case? So we can say in that case, rather than, so gradient may not be 0. Okay, that's possibility in the random variable case. But what you can say is that the variance of the gradient is supposed to be 0. Okay, so everywhere we are kind of extending the classical definition. Okay, so classical definition said that interpolation holds, then fi x star is 0, hence grad. The x star is the minima of fi, hence the gradient should vanish, obviously. Here we cannot say directly. We say instead of gradient being vanishing, we will say the variance of the gradient vanishes. Okay, these are the changes we have to do in the stochastic case. So the third one, interpolation holds, then sigma star f is 0, right? Okay, as I keep saying, right, you just have to see these things once, and after that, you, when things are new, it always looks strange. Okay, it's a very common thing, right? So if interpolation holds, then, so that's like the definition, right? So if then there exists, so this is from lemma 4.10. Then there exists x in argmin. What you can do is that you can get a print of this notes. We will be doing this for another 2-3 classes, so that will be easier to refer in the class. Okay, so then x in argmin of f such that x star is in argmin of fi for every I equal 1 to n. So if interpolation holds, then there exists an x in argmin such that, is this x in argmin or x star in argmin? X star, right? Why should we have x? So there exists x star in argmin which interpolates to each of the individual fi, right? Okay, so obviously gradient must vanish, right? Because x star is a minima of fi. So obviously, so this implies that gradient of fi x star is 0, because x star is a minimum of fi. That's what that's where the gradient should be flat, and then and also since it's for the f, so grad f x star is 0. So now what about the variance? So variance obviously will be 0 only, right? So variance of grad fi x star is, which is defined to be expectation of gradient of fi x star minus gradient of x star. Okay. So the way we defined is that this happens to be the expectation. Okay, just to we wrote it in one line. Okay, so which was nothing but expectation of grad of fi x star. The variance is defined to be this minus expectation of this whole square, but expectation happens to be the f. So that's what we did, and then since these grad fi's are 0, these expectation is supposed to be 0. And again, I believe the same argument that basically this is 0 directly. Grad fi x star is 0 because we are supposed to prove sigma star f is 0. What we have proved is the variance of grad fi x star is 0. And since for all I it's 0, infimum will also be 0, right? So I mean this is for any x star, so it's 0, right? So this proves that sigma star f is 0. Now that's all, right? I mean I don't know why the proof goes on a little bit more. So it says now if the assumption sum of convex holds and sigma star f is 0, then we can use the previous item to say that for any x star in argument of f we have variance of grad f x star is 0. Okay, then by definition of the variance and the fact that this implies that for every I grad f I is 0. The final conclusion is which means that the interpolation holds. This was not if and only if, right? Is it? Oh, okay, the additional thing is like this becomes an equivalence. Okay, I believe this is an exercise for you. Okay, this is just few lines again, you can have a look. Okay, so actually this becomes an equivalence. The other way is also true. If it happens to be sum of convex, then sigma star f being 0 also implies that interpolation holds. So if for sum of convex sigma star f equals to 0 implies that the interpolation holds. Okay, let's stop for today. Okay, thanks.